What if Earth had rings like Saturn? At first, it sounds almost poetic, a glowing band of light stretching across the sky, turning every night into a celestial spectacle. But beauty in the cosmos often comes with a cost. Such a ring wouldn't just be decoration. It could reshape climate, disrupt ecosystems, and even alter the course of evolution itself. The sky we take for granted might have once been something entirely different, brighter, harsher, and far more dangerous. Before we go deeper, if you're fascinated by hidden cosmic histories and the forces that quietly shape our world, consider subscribing and following the channel. Because stories like this don't just change how you see the sky, they change how you understand Earth itself. And to begin understanding how something like a planetary ring could form around Earth, we need to look far beyond our planet, to a dramatic event that unfolded in 1994. That year, a fragmented comet known as Comet Shoemaker-Levy 9 collided with Jupiter. But by the time scientists observed it, the comet was no longer a single object. It had already been torn apart into more than 20 pieces, stretched into a chain by Jupiter's immense gravitational pull. This was no ordinary collision. Each fragment slammed into Jupiter's atmosphere at speeds exceeding 200,000 kilometers per hour. The impacts released energy equivalent to millions of nuclear explosions. Fireballs erupted thousands of kilometers above the cloud tops, leaving dark scars so large they rivaled the size of Earth itself. And yet, what mattered most wasn't just the destruction, it was the process that led to it. Jupiter didn't simply attract the comet, it dismantled it. As the comet passed too close, tidal forces, the difference in gravitational pull across its structure, became overwhelming. The side closer to Jupiter was pulled more strongly than the far side, stretching the comet until it fractured. What had once been a single icy body became a string of debris, each piece following its own fatal path. Now imagine a slight change in that story. What if the comet hadn't plunged directly into Jupiter? What if its trajectory had been just stable enough to avoid immediate collision? Instead of spiraling inward to destruction, those fragments might have spread out, forming a ring, a halo of ice and rock orbiting the planet. Not a brief catastrophe, but a long-lived structure. This is where the idea becomes more than speculation. Because this alternative outcome isn't hypothetical, we already see it elsewhere. Look at Saturn, the most iconic example of planetary rings in our solar system. Its rings are not solid structures, but vast collections of particles, ranging from microscopic dust to chunks the size of mountains. They orbit in a delicate balance shaped by gravity, collisions, and time. But Saturn's rings don't maintain themselves. They are constantly at risk of dispersing into space or collapsing inward. What keeps them stable are its so-called shepherd moons, small satellites like Prometheus and Pandora that orbit near the edges of the rings. Their gravitational influence acts like invisible boundaries, corralling particles and maintaining the ring's structure. Without these moons, the rings would gradually fade away. This comparison reveals something critical. Rings are not rare accidents. They are natural outcomes of gravitational systems under the right conditions. A close encounter, a disrupted body, and a stable orbit. That's all it takes. Which raises an unsettling possibility. If a comet can be torn apart by Jupiter, and if Saturn can maintain vast rings for millions of years, then under the right circumstances, Earth could have experienced something similar. Not as a permanent feature perhaps, but as a temporary phase, an era when our planet was surrounded by a dense field of orbiting debris. And if that ever happened, the consequences would have been profound. A ring around Earth wouldn't just glow in the sky. It would cast shadows across the planet, reflecting sunlight during the night and blocking it during the day. It would slowly rain debris back into the atmosphere, triggering continuous meteor impacts. Entire regions could be repeatedly destroyed and rebuilt, ecosystems reset again and again under a sky that never quite looked the same. And the story of Shoemaker-Levy 9 shows us the raw power of gravity, the ability to break worlds apart. Saturn shows us what happens when that destruction is stabilized instead of completed. And between those two extremes lies a narrow possibility, one that may have shaped Earth in ways we are only beginning to understand. Because sometimes the difference between annihilation and transformation is not the force itself, but the path it takes. If the idea of Earth once wearing a ring still feels distant, almost speculative, the next step in this story brings it much closer, down from the scale of planets to something far more tangible: stones that have literally fallen from the sky. On the night of December 24th, 1965, in the quiet village of Barwell, something extraordinary happened. A brilliant doe streaked across the sky, brighter than any star, moving too fast and too deliberately to be mistaken for anything familiar. Seconds later, a sonic boom shattered the silence. Windows rattled. The ground seemed to tremble. And then came the impacts, sharp, sudden, scattered across rooftops, roads, and fields. What had just occurred was not a single meteor strike, but a full meteorite shower. Fragments of a single object had broken apart in the atmosphere and rained down over the village. By the next morning, the scale of the event became clear. Small craters marked the ground. Pieces of dark, glassy rock lay scattered across the landscape. One fragment had even punched through a car, damaging it beyond repair. And in total, more than 40 kilograms of extraterrestrial material were recovered. These were not ordinary stones. They were ancient, formed over 4.5 billion years ago, older than Earth itself. For scientists, this event was invaluable. It demonstrated something simple but powerful. Under the right conditions, space debris can fall not as isolated incidents but as widespread, concentrated showers. But Barwell, remarkable as it was, only hinted at a much deeper mystery. To find that, we have to travel to a limestone quarry in southern Sweden, Thorsberg Quarry. At first glance, it seems unremarkable. Layers of ancient rock formed hundreds of millions of years ago beneath a warm, shallow sea. But in 1988, workers cutting through these layers uncovered something strange. Dark, dense inclusions unlike the surrounding stone, with a texture and composition that immediately stood out. These were not just rocks embedded in rock, they were fossilized meteorites. Over the following years, scientists conducted systematic searches of the quarry. What they found was astonishing. More than 40 fossil meteorites within a relatively small area. But the real surprise wasn't just the number, it was how they were distributed. These meteorites were not clustered in a single layer, as you would expect from one catastrophic event. Instead, they were spread across multiple geological strata, representing a timeline that stretched over nearly 2 million years. This changed everything. Normally, meteorites fall to Earth at a relatively low and random rate. In a given area, over such a time span, you might expect to find one or two. But here, the density was dramatically higher, far beyond what standard models could explain. It suggested that during that period, Earth was being bombarded at a rate 10 to 100 times greater than today. And then came the most revealing detail of all. When scientists analyzed the chemical composition of these fossil meteorites, they found something striking. They were almost identical. Nearly all of them belonged to a specific class known as L-chondrites, stony meteorites with relatively low iron content. This wasn't just a coincidence. Meteorites that fall at different times and places usually come from a variety of parent bodies. But here, the uniformity pointed to a single origin, a single source, a single event. The same composition was found in many modern meteorites as well, including those from Barwell. Even today, a significant proportion of meteorites that reach Earth belong to this same category. It's as if fragments from one ancient catastrophe are still arriving, echoing across time. So what could produce such a prolonged, concentrated influx of material from a single source? The answer leads us to one of the most dramatic hypotheses in planetary science, the destruction of an entire celestial body. Roughly 470 to 500 million years ago, somewhere between the orbits of Mars and Jupiter, there likely existed a large asteroid or perhaps even a small planet. And this body, now referred to as the L-chondrite parent body, had formed early in the history of the solar system, alongside the planets themselves. For billions of years, it remained relatively stable, orbiting quietly within what is now the asteroid belt. But stability in the solar system is never permanent. Over time, Gravitational interactions, especially from Jupiter, can destabilize orbits. Small perturbations accumulate, pushing objects into new paths. Eventually, this ancient body was likely nudged into a catastrophic collision. Whether it struck another large asteroid or was torn apart by tidal forces, the result was the same: total destruction. The body shattered into millions of fragments. Some of these fragments remained in the asteroid belt, forming families of smaller bodies, but others were flung inward toward the inner solar system. And among those fragments, some began trajectories that would intersect with Earth's orbit. At first, this would have resulted in an increased rate of impacts, exactly what we see recorded in the Thorsberg Quarry. But the hypothesis doesn't stop there, because under very specific conditions, something even more unusual could have occurred. Imagine one of these fragments, not a small piece but a massive chunk, approaching Earth on a near-miss trajectory. Instead of colliding directly, it passes dangerously close, at a distance of perhaps 15,000 kilometers. That's closer than many modern satellites orbit today. At that distance, Earth's gravitational field would not simply pull the object inward, it would tear it apart. And just like Jupiter did to Shoemaker-Levy 9, tidal forces would stretch and fracture the body. The side facing Earth would be pulled more strongly than the far side, creating immense tonneau within the structure. Rock would crack, sections would break free, the object would disintegrate into a cloud of debris. But here's the critical difference. Instead of plunging into the atmosphere, much of that debris could enter orbit. Captured by Earth's gravity, these fragments would spread out along the path of the original object, gradually forming a ring. Not instantly, but over time, a shifting, evolving band of rock encircling the planet. Some fragments would collide with each other, breaking into smaller pieces. Others would slowly spiral inward, eventually falling to Earth as meteorites. This scenario provides a unifying explanation for multiple lines of evidence. It accounts for the prolonged meteorite influx recorded in ancient rocks. It explains the shared chemical signature of those meteorites. And it offers a mechanism for how Earth could have temporarily acquired a ring system, one born not from gentle accumulation, but from violent disruption. If this is what happened, then the sky above Earth during that time would have been unlike anything we can imagine today. A luminous arc stretching across the heavens. A constant reminder that the planet was not isolated, but embedded in a dynamic and sometimes dangerous cosmic environment. And more importantly, it suggests that the story of life on Earth may have been shaped, not just by conditions on the surface, but by events unfolding far beyond it. If such a ring truly formed around Earth, it would not have been a fleeting phenomenon. The evidence suggests something far more enduring, an entire chapter in the planet's history that may have lasted on the order of tens of millions of years. Estimates point to roughly 40 million years, a span so vast that generations of life would have evolved, adapted, and vanished beneath a sky permanently altered by orbiting debris. This was not a thin, delicate structure like a faint halo. It would have been dense enough to be seen clearly from the surface, an immense band of rock and dust encircling the planet. And from certain latitudes, it might have appeared as a brilliant arc stretching from horizon to horizon, fixed in the sky yet shifting subtly with the seasons. Near the equator, it would cut across the heavens like a luminous scar. Closer to the poles, it would cling to the horizon, a constant, glowing presence. And it would have been bright, far brighter than anything we see in the night sky today. Unlike the moon, which waxes and wanes, this ring would reflect sunlight continuously. Even in the deepest night, it could cast a diffuse glow across the landscape, softening shadows and erasing true darkness. The concept of a dark night might not have existed at all during this period, and instead, there would have been a perpetual twilight, punctuated only by the shifting brightness of the ring as Earth rotated beneath it. But this beauty would have come with relentless consequences. A ring is not a static object. It is a dynamic system, constantly evolving. Particles collide, fragment, and gradually lose energy. Over time, many of them spiral inward, pulled by atmospheric drag and gravitational interactions. For Earth, this would have meant a continuous rain of material, an unending cascade of meteorites entering the atmosphere. Unlike isolated impacts separated by thousands of years, this would have been a sustained bombardment. Small fragments would burn up as streaks of light, turning the sky into a constant display of falling stars. Larger pieces would survive the descent, striking the surface with explosive force. Regions of the planet would be repeatedly disrupted, landscapes reshaped over and over again. This persistent influx of debris would have made impacts a routine part of Earth's environment. Entire ecosystems could be erased locally, only to recover and evolve again before the next wave arrived. It was not a single catastrophe, but a prolonged state of instability, a world in which destruction and renewal occurred side by side. At the same time, the ring would have influenced something even more fundamental: the flow of energy from the sun. By its very nature, a dense ring system would block and scatter sunlight. Depending on its thickness and orientation, it could cast partial shadows across the planet. And these shadows would not be constant. They would shift with Earth's rotation and orbit, creating complex patterns of a dough and shade that changed over time. Some regions might experience reduced sunlight during certain parts of the year, while others remained fully exposed. This effect, subtle on a daily scale, could become significant over millions of years. To understand its impact, we need to consider the state of Earth during the Ordovician period, roughly 485 to 444 million years ago. At that time, the planet was fundamentally different from today. Atmospheric carbon dioxide levels were extraordinarily high, many times greater than modern concentrations. This greenhouse gas trapped heat efficiently, driving global temperatures upward. The result was a warm, almost tropical world. There were no permanent ice caps at the poles. Sea levels were high, flooding continental margins and creating vast shallow seas rich in life. The oceans teemed with organisms, and early ecosystems were expanding rapidly. From a climate perspective, Earth was operating near the upper limits of habitability. Under such conditions, there was a real risk of a runaway greenhouse effect, a feedback loop in which rising temperatures cause more heat to be trapped, leading to further warming, and so on. This is the process believed to have transformed Venus into the hostile world we see today. And yet, Earth did not follow that path. Despite the high levels of carbon dioxide, global temperatures eventually stabilized and even began to decline. And something acted as a counterbalance, preventing the system from spiraling out of control. This is where the ring hypothesis becomes especially intriguing. A planetary ring, by partially shading the surface, could have reduced the amount of solar radiation reaching Earth. Even a small decrease in incoming energy, sustained over millions of years, could offset the warming influence of greenhouse gases. In effect, the ring may have functioned as a tabi'i sunshade, an orbital veil moderating the planet's climate. But like many natural systems, this balance would have been delicate. The cooling effect of the ring would not have been uniform. Variations in its density, combined with Earth's axial tilt and orbital changes, could have produced uneven patterns of temperature change, and some regions might cool more rapidly than others. Seasonal contrasts could intensify. Ocean circulation patterns might shift in response to changing temperature gradients. Over time, these imbalances could accumulate. What begins as a stabilizing influence can, under the right conditions, become a destabilizing one. If the cooling effect grew too strong, it could push the climate system past a critical threshold. Ice, once it begins to form, reflects sunlight, reinforcing the cooling trend. This positive feedback can accelerate rapidly, transforming a warm world into a cold one in geological terms. In this way, the same ring that may have helped prevent a runaway greenhouse effect could also have set the stage for a dramatic reversal, a transition toward global cooling and glaciation. The Ordovician climate record hints at exactly such a shift. After millions of years of warmth, the planet experienced a sudden and significant drop in temperature. Ice sheets began to form, sea levels fell, and environments that had supported diverse life were drastically altered or destroyed. While many factors likely contributed to this proverton, the presence of a ring system offers a compelling piece of the puzzle. It provides a mechanism capable of influencing climate on a global scale, sustained over the right time frame, and consistent with the evidence of prolonged meteorite influx. If this interpretation is correct, then the ring was not just a passive feature of the sky, and it was an active agent in Earth's history, a structure that shaped the balance between heat and cold, stability and chaos. For tens of millions of years, life on Earth may have existed under its shadow, adapting to conditions that were constantly shifting, never fully stable. And in that unstable environment, the seeds of both flourishing and collapse were quietly being sown. Under a sky crossed by a permanent band of debris, life on Earth would not have unfolded in a calm, predictable way. Instead, it would have existed in a state of postoyanner tension, caught between destruction and renewal. And paradoxically, it may have been precisely this instability that fueled one of the most remarkable expansions of life in our planet's history. And during the Ordovician period, the fossil record reveals an extraordinary surge in biodiversity. Marine ecosystems in particular became vastly more complex. New species appeared at an accelerated pace, filling ecological niches that had never existed before. Seafloors that were once relatively simple became crowded with organisms of every shape and function: filter feeders, burrowers, predators, and early vertebrate ancestors. This was not just gradual evolution, it was an explosion. At first glance, such rapid diversification seems difficult to explain. Stable environments typically support incremental change, not sudden bursts of innovation. But the conditions created by a ring system and the constant influx of debris would have been anything but stable. Each impact, whether large or small, acted as a localized reset button. When a sizable fragment struck the ocean or a shallow sea, the immediate effect was catastrophic. Water would vaporize, shockwaves would ripple outward, devastating surrounding Al-Hayat. Entire communities of organisms could be wiped out in moments. Sediments would be churned, chemistry altered, and habitats fundamentally transformed. But destruction was only the beginning. In the aftermath of an impact, the environment did not return to its previous state. Instead, it became something new. The seafloor might be deeper or shallower. Mineral compositions could shift, changing the availability of nutrients. Temperature gradients might be altered, influencing currents and oxygen distribution. What emerged was not a restoration, but a reconfiguration. And in that reconfiguration lay opportunity. Species that had once dominated might no longer be suited to the altered conditions. Meanwhile, others, previously marginal or rare, could suddenly thrive. Over time, as impacts continued to occur across different regions, the planet became a mosaic of evolving ecosystems, each at a different stage of destruction and recovery. This patchwork dynamic is crucial. Instead of a single, uniform biosphere, Earth would have supported countless micro-environments, constantly being reset and reshaped. Evolution, under these conditions, accelerates. Natural selection acts more intensely when environments change rapidly. Traits that allow flexibility, resilience, or rapid reproduction become advantageous. New species emerge not just from slow adaptation, but from repeated cycles of duct and release. In this sense, the ring system may have functioned as a catalyst for biological innovation. It didn't create life, but it created the conditions under which life could diversify more quickly than usual. The Ordovician biodiversity surge, sometimes referred to as one of the great radiations of life, may owe part of its intensity to this relentless cycle of disruption and renewal. Yet the same mechanism that drives expansion can also set the stage for collapse. As the ring continued to influence Earth's climate, its cooling effect, subtle at first, would have persisted over millions of years. Gradually, the balance began to shift. Atmospheric carbon dioxide levels, once extremely high, started to decline, whether through increased weathering of rocks, biological processes, or other awamil. The greenhouse effect weakened. At the same time, the partial shading caused by the ring continued to limit incoming solar energy. Eventually, these influences converged. Global temperatures began to fall. What had once been a warm, ice-free world started to cool significantly. Ice sheets formed on the southern supercontinent, spreading outward and locking vast amounts of water away from the oceans. Sea levels dropped, exposing shallow marine habitats that had been crucial for much of the existing biodiversity. For marine life, this was devastating. This shallow seas had been the cradle of Ordovician ecosystems. As water retreated, entire habitats vanished. Organisms adapted to stable, warm conditions suddenly faced colder temperatures and shrinking prostranstva. At the same time, changes in ocean circulation disrupted the distribution of oxygen. In many regions, oxygen levels fell dramatically. This created vast zones of anoxia, areas where oxygen was too scarce to support most forms of life. Creatures that could not adapt to these conditions simply perished. The combination of habitat loss, temperature change, and oxygen depletion proved overwhelming. The result was one of the most severe mass extinctions in Earth's history. Approximately 85% of marine species disappeared. Entire groups of organisms were wiped out, their evolutionary experiments cut short. Ecosystems that had taken millions of years to develop collapsed in a relatively brief geological moment. The vibrant, diverse seas of the early Ordovician gave way to a much simpler, diminished world. What makes this event particularly striking is its suddenness. For tens of millions of years, conditions had supported expansion and diversification. Then, within a comparatively short time, those same systems failed. The direct causes, glaciation, falling carbon dioxide levels, and oxygen depletion, are well supported by geological evidence. But the underlying trigger remains a subject of debate. Why did the climate shift so abruptly? What pushed the system past its tipping point? Here again, the ring hypothesis offers a compelling perspective. If a ring system had been gradually reducing solar input over millions of years, its effect might have accumulated slowly, almost imperceptibly. Unlike a sudden cutna, such as a massive asteroid impact, this would be a long-term influence, subtle but persistent. Over time, it could have nudged the climate toward instability, making it increasingly sensitive to other factors. Then, when carbon dioxide levels dropped, the system may have crossed a critical threshold. In this scenario, the ring does not act alone. It is part of a network of interacting processes, atmospheric, geological, and biological, but its role is significant, and it provides a mechanism for sustained global cooling aligned with the timescale of the observed changes. Perhaps most intriguingly, it suggests that the same structure that helped drive the diversification of life also contributed to its destruction. This dual role, creator and destroyer, is a recurring theme in Earth's history. Forces that generate complexity often carry within them the seeds of collapse. In the case of the Ordovician, the ring system may have amplified both sides of that equation, accelerating evolution through repeated disruption and later tipping the climate toward a state that life could not sustain. If so, then the story of Earth's ancient ring is not just about a feature in the sky, and it is about how external cosmic processes can shape the deepest patterns of life, determining not only how it grows but how it ends. As compelling as the ring hypothesis is, it does not exist in isolation. The deeper scientists look into the Ordovician world, the more they uncover alternative explanations, some subtle, others almost unimaginably violent. These additional hypotheses do not necessarily contradict the idea of a planetary ring, but they expand the landscape of possibilities, reminding us how many forces, both terrestrial and cosmic, can converge to reshape a planet. One of the most dramatic proposals reaches far beyond the solar system itself, the possibility of a gamma-ray burst. A gamma-ray burst is among the most powerful phenomena known in the universe. In a matter of seconds, it can release more energy than our sun will emit over its entire lifetime. If such a burst were directed toward Earth from relatively close range within our galaxy, its effects could be devastating. High-energy radiation could strip away parts of the atmosphere, damage the ozone layer, and expose the surface to lethal ultraviolet radiation. In theory, this could trigger widespread biological stress, particularly in shallow marine environments where life is most exposed. Some researchers have suggested that such an event might explain sudden disruptions in biodiversity, including those seen at the end of the Ordovician. But here, the evidence becomes uncertain. Unlike meteor impacts or glaciation, which leave clear geological signatures, gamma-ray bursts are far more difficult to detect after the fact. There are no craters, no direct physical remnants, only indirect clues, such as unusual chemical isotopes or patterns of extinction that might align with radiation exposure. So far, no definitive evidence has been found linking a gamma-ray burst to the Ordovician extinction. It remains a fascinating but unconfirmed possibility, a reminder that not all cosmic influences leave visible scars. Closer to home, another hypothesis brings the focus back to Earth itself, but on a scale that is almost equally dramatic. And in recent years, geophysical surveys in Australia have revealed the outline of a Vishal, deeply buried structure, one that may represent an enormous ancient impact site. Known as the Deniliquin structure, this formation spans hundreds of kilometers, making it potentially one of the largest impact features ever identified on Earth. Unlike more familiar craters, which are clearly visible at the surface, this structure lies hidden beneath layers of rock, detectable only through subtle variations in gravitational and magnetic fields. Its size suggests an impact of extraordinary magnitude, far exceeding most known collisions in Earth's history. If confirmed, such an impact would have released energy on a scale capable of altering global systems. The shockwaves would have propagated across the planet. Massive quantities of dust and aerosols could have been injected into the atmosphere, reducing sunlight and cooling the climate. Ocean chemistry might have been disrupted and ecosystems pushed to their limits. What makes this hypothesis particularly intriguing is its possible timing. Some interpretations suggest that the Deniliquin structure could date back to roughly the same period as the Ordovician extinction. If that connection holds, it raises a provocative question. Could this impact have been linked to the same debris field that formed Earth's hypothetical ring? In other words, could a fragment from that ring, perhaps a larger, more stable piece, have eventually spiraled inward and struck the planet with catastrophic force? If so, the ring would not only have influenced Earth gradually through climate and meteor showers, but also delivered a final, निर्णायक blow through a single, massive collision. It would represent a continuum of effects, from subtle to extreme, all originating from the same cosmic event. Yet, as with the gamma-ray burst, certainty remains elusive. Dating such ancient structures is complex and the evidence is still being debated. And the Deniliquin structure may indeed be an impact site, or it may represent a different geological process altogether. For now, it stands as a tantalizing clue, not a confirmed answer. And perhaps that is the most important realization to take from this entire story. We are looking back across hundreds of millions of years, trying to reconstruct events that left only fragments of evidence, rocks, alchemia, patterns in the fossil record. From these fragments, scientists build models, test hypotheses, and refine their understanding. But complete certainty is rare. What we gain instead is a framework of possibilities, each supported by different lines of evidence, each contributing to a more nuanced picture of Earth's past. And when we step back and consider the full scope of the argument, a striking pattern emerges. A ring system around Earth, formed from the razrashani of a distant planetary body, could have created a prolonged period of instability. It would have driven a sustained influx of meteorites, repeatedly resetting local ecosystems. It may have moderated global temperatures, preventing a runaway greenhouse effect in a world rich in carbon dioxide. And over time, it could have contributed to a gradual cooling trend that culminated in glaciation. In this view, the ring becomes both a creator and a destroyer. It fosters diversity by forcing life to adapt, to innovate, to occupy new niches as old ones are erased. But it also pushes the planetary system toward thresholds, points beyond which stability cannot be maintained. When those thresholds are crossed, the result is collapse on a massive scale. This duality is not unique to the Ordovician. It reflects a broader principle in Earth's history. The forces that drive change are often the same ones that impose limits. Volcanism can create fertile land and enrich the atmosphere, but also trigger climate behran. Impacts can destroy ecosystems, but open pathways for new ones to emerge. And perhaps, as this hypothesis suggests, even something as seemingly distant as a ring of debris in orbit can shape the trajectory of life below. The implications extend beyond the past, and they remind us that life on Earth is not governed solely by conditions at the surface. It is part of a larger system, one that includes gravitational interactions, orbital dynamics, and events occurring across vast distances. The boundary between Earth and space is more permeable than it appears. What happens in orbit, or even beyond the solar system, can ripple inward, influencing climate, evolution, and survival. And this leads us to the questions that remain unanswered. Did Earth truly possess a ring system? And if so, how dense and long-lived was it? Was it a dominant force in shaping Ordovician climate, or just one factor among many? To what extent did it contribute to the eventual mass extinction? And could similar processes occur again under different conditions? These are not simple questions, and they may never have definitive answers. But they point to something deeper, a recognition that our planet's history is intertwined with the dynamics of the cosmos in ways we are only beginning to understand. If a ring once circled Earth, it would have been a spectacular sight, an ever-present arc of light across the sky. But beyond its beauty, it would have been a force of transformation quietly shaping the fate of life below. And perhaps the most profound realization is this: the story of Earth is not just written in its rocks and oceans, but also in the invisible forces that surround it, forces capable of creating worlds and unmaking them just as easily.